All right, let's get started. Before we get started with talking about the material from Class D, a couple reminders. Reminder one, we don't have class on Monday, meaning just this class. I will not be here on Monday. Your other classes still meet on Monday, but we are not having class on Monday. So don't come here on Monday at 10 o'clock. I won't be here. Don't be here. I also won't be having office hours on Monday because I won't be here on Monday. The other thing I wanted to say was we do have a quiz today. It's available starting after class at 11, and it's available until Sunday at 11 p.m. It's kind of like a homework assignment in that you will do it in the same way. You'll do it on Gradescope. You'll submit it on Gradescope. The difference is it is timed. So once you start it on Gradescope, you will have 40 minutes to finish it. That includes scanning and uploading it. That should be in more than enough time, but make sure you use your time efficiently. If you run into any issues, let me know right away. Send me an email. I'm usually pretty responsive. The other thing I wanted to point out is if you look at Canvas over here. By the way, just so you all know, in case you didn't know, you can change the name of your class in Canvas. So if you want to change it to something else, you can click that little button there and then change the name right there. I changed the name so they say like the time and the CRN number because that piece of information is useful to me. If you want to change the name to something else that's more useful to you, you totally can. But if you go to our class, and then you can either, I would say just go to the modules and scroll down to quiz 1. Ways down, okay, keep scrolling, okay, quiz 1. There's a practice quiz 1, there's practice quiz 1 solutions. I definitely encourage you to look at both of those things before you do the first quiz. And then after that, check out the first quiz. This won't start the quiz, clicking on that. If you look at there's some instructions. Make sure you know how to let's see, before you take the quiz, make sure you have paper and pencil to write your answers on. You are welcome to print out the quiz, but you do not have to print out the quiz. You can just write your answers to the quiz on another piece of paper. You don't have to rewrite the questions. I know what the questions are. The questions are there. So don't use your time writing out the questions because you don't need to. Make sure you're ready and know how to scan and upload your results to Gradescope. So if you've already turned in the first homework assignment, you know how to do that already. It's the same kind of deal. And then make sure you know make sure you know all the, I don't know why the word how is there. Make sure you know all about lines, parabolas, and circles. I might write a little bit more there before, right after class to be a little more explanatory about the things you should know. But if you look at the practice quiz, you'll have a very good idea of what's on the actual quiz. So I would encourage you all to look at the practice quiz before you do the actual quiz. Questions about that? And then you can either click on this. It won't load it for me now because 1, I'm not a student in the class, and 2, it's not available yet. And you can click on that, it'll take you to the quiz in Gradescope, and then you can start it there. You can look at the outline if you want to. Yeah, you'll need to look at the outline, except for the quizzes. And you should be able to see it. If you run into any issues at all, shoot me an email right away. I will respond rapidly. I saw a hand. Yeah. It is not based on optimization. It is completely based on just the stuff in homework A/B. There are no optimization problems on this quiz. Other questions? So like today's class, it totally will not apply to the quiz. Totally fine. You should still be here. Any other questions? If you think of another question comes up later, you're always welcome to ask or to send me an email asking whatever you like. Oh, okay, sure. Fine. Anybody on Zoom have any quiz questions? Again, you're always welcome to ask. All right. I also have office hours today from 3 to 4 p.m. in CADS. That's over in the 2nd floor of the South Silo. So if you're looking for some assistance, you can come find me there this afternoon. I'll probably be there like 3:10 because I have a class right before that and it's a whole bit of a walk. So 3:10 to 4-ish. All right, let's do it. Let's talk about Class D, which is really just more optimization. So I imagine we might finish early. I should never say that because I sometimes imagine we will finish early and then we never do. So you might finish early, we probably won't, because I can just talk and talk and talk. So this is very much the same situation as class on Wednesday, meaning we're still looking at the same kind of problems, we're doing the same kind of setup, we're trying to find a thing we're going to either maximize or minimize, and usually we're going to do that by finding some or all of the vertex of a problem. Right? That's kind of the only way we are able to maximize or minimize functions at this stage. So let's read the problem. A rancher wants to build an enclosure for his animals. The fencing material for 3 sides costs $2 per foot, and the material for the 4th side costs $1 per foot. No one said anything about it, but if someone's building an enclosure for animals and they didn't say what it was, what's the shape we're probably thinking it's going to be? A rectangle. Not necessarily a square, although it could be a square, but definitely if no one's saying what the shape is, it's going to be a rectangle, especially if it's got 4 sides. I'm not going to have you build a triangular corral. I'm not going to have you build a pentagonal corral. It's going to be a rectangle. And it might end up being a square, which is a rectangle. It's just a nicer rectangle. So 3 of the sides of this corral cost $2 per foot, and the 4th side costs $1 per foot. If the rancher can only afford to spend $500 on the enclosure, by the way, when I read that, what I'm automatically thinking is, oh, that's my constraint. I am limited by how much money I can spend. What dimension should the rectangle be to maximize the total area? So let's draw a picture. Let's draw a rectangle. I'm going to label the sides with variables. I'm going to pick, it doesn't really matter. I'm going to call this side X and this other side Y. And it's kind of a weird situation because a lot of the times in problems like this, like the X sides are the same cost and the Y sides are the same cost, but that's not the situation. We've been told that 3 of the sides cost $2 per foot, and 1 of the sides costs $1 per foot. So we just kind of have to pick which side is going to be the $1 side. It doesn't actually matter. So if I pick the $1 side to be one of the Y sides, whatever I end up getting for Y will be a certain number. If you instead pick the $1 side to be one of the X side, it just means that our answers are going to look switched, meaning my X and Y values will be the interchange of your X and Y values. So it doesn't actually matter which way you pick it. You just have to make a choice. So I'm going to say, I'm going to say that this is the side that costs $1 per foot. And these other sides are the $2 per foot sides. This is $2 per foot. This is $2 per foot. This is $2 per foot. All right, so let's see here. I'm being asked to, I always look for the thing I'm trying to optimize for. So there's always 2 pieces to these optimization problems. There's the thing you're trying to maximize or minimize, and there's the constraint. And I, for some reason, think it's a good idea to write down the thing you're trying to optimize first. But if you write down the constraint first, that's also okay. So we're trying to maximize what? Yeah. We want to maximize area. Great. The equation for area. So the area here is just area equals X times Y. It's pretty typical for a rectangle. The constraint here is a little bit harder than it was on Wednesday. On Wednesday, we were given the constraint that we only had so much fence to use. So like on Wednesday, if this problem instead said, you know, I only have 600 feet of fence to use, I would say my constraint is X plus Y equals 600. Or 2X plus 2Y equals 600. Here, though, I have to do a little bit more because I'm not constrained by the amount of fence I have. I'm constrained by the amount of money I have. So my constraint really has to do more with the cost. So my constraint is based on how much this fence is going to cost. So let me ask you all a question. Let's say we did all the work. We got some pretend numbers for answers. Let's say this side ended up being 100 feet long. That X side. How much did that side cost to build if it was 100 feet long? $200, right? Because you multiply the number of feet by $2 per foot. Well, we don't know that it's actually 100 feet. We've called it X feet long. So it's going to cost $2 times X, because that's how much feet we have times the price per foot. So the constraint is going to be that we have $2 times X plus $2 times Y plus another $2 times X plus $1 times Y is equal to, I have $500 to spend. And I'm going to spend it all. Now, of course, you can skip this not simplified version and go straight to, well, I know I have 2X plus 2X is 4X, and 2Y plus 1Y is 3Y equals 5. Okay, so now you have a choice. Do you want to isolate Y or isolate X? you can pick Y, you can pick X. Either way is going to be fine. I might personally choose to pick X because dividing 500 by 4 divides somewhat nicely, whereas dividing 500 by 3 does not. Either choice is going to be fine then. So if I isolate X, because that's what I decided I wanted to do, we're going to get 4X equal to negative 3/4 Y plus 500. And then we're going to get X. Oops. Oh, I got ahead of myself there. I started dividing by 4 too soon. I guess I'll write this over here. I'll have 4X equal to negative 3Y plus 500. And then if I divide everything by 4, I'll have 4X divided by 4 equals negative 3/4 Y plus 500 divided by 4. That saved it. Okay. And then what's 500 divided by 4? Right. And if you're having trouble dividing by 4, what I just do is divide by 2 twice. 500 divided by 2 is 250. 250 divided by 2 is 125. That's kind of, I think it's easier than dividing by 4 personally. So I've got X equal to negative 3/4 Y plus 125. All right, so now I'm going to throw that back in to the thing I'm trying to maximize. So now I really want to maximize up a little bit. I'm trying to maximize area equal to negative 3/4 Y plus 125 times Y, which I am going to multiply out so that I can see what the A and B are in my parabola. Now, a lot of these ones work out that this ends up being the A and that ends up being the B. You should still do the multiplying. That's going to be negative 3/4 Y squared plus 125 Y. Okay, so now we're going to find the vertex. And so this is where, again, right, the language of the notation can be a little bit confusing. We're going to find the first coordinate of the vertex, but that's my Y value, right? Maybe it would have been better to use X because it would have been less confusing, but actually I don't think that's true. So I don't want you to be married to the fact that the first coordinate has to be X. It doesn't. The first coordinate is your input variable. The second coordinate is your output variable. If I was thinking about graphing this parabola, let me grab another piece of paper here real quick. If I was thinking about graphing this parabola, which I might do in a second here, I'd be thinking, okay, my horizontal axis is the Y axis because that's what I'm inputting, and my vertical axis is the area axis because that's my output. That's my input. It's a little annoying sometimes, but it's the truth is that that's how we're usually thinking of things. So I'm trying to find my input coordinate of the vertex. I know I really don't love the notation here, but I'm going to find the Vy of Vy comma Va, just to make it more clear that that's my X coordinate, that's my Y coordinate. Okay, so usual stuff. The input coordinate is negative B over 2A, which is negative 125 divided by 2 times negative 3/4. Wow, that is not fun. That's going to equal, let's see, so 2 times negative 3/4 is going to be negative 3/2. The negatives will also cancel out. So let's say we've got 125 over 3/2, and then I'm going to flip and multiply. I get 125 times 2/3, which is 125 over 1 times 2/3, which is 250 thirds. And that is my Y value. And that doesn't simplify any further. You can write it as a decimal if you want. It is a repeating forever decimal. It's 83.333333, right, forever, never, never. I don't want to write it that way. I typically would encourage all of you to preference writing things as fractions over decimals. It's usually just nicer. Sometimes decimals are better, but whatever. All right, now so this is the stage where we found the input coordinate of the vertex. And then what do I think we should do next? I hear a few things, but I didn't know. My hearing is not always best. I'm just going to say the thing I think we should do next, which is We go back and read the question to find out if we've answered it correctly or if what we still need to do. So if I go back and read the question and look for what they're actually asking us for, they're asking us what dimensions should the rectangle be to maximize the area? Oh, you can't see that. What dimensions should the rectangle be to maximize the total area? So they're asking us for X and Y. They're not asking us for the area. So I'm going to go back and say, well, look, there's X right there. X equals -3/4 Y plus 125. So if I plug in this value for Y, and hopefully I can squeeze this in here, X is going to equal -3/4 times 250 thirds plus 125. Simplifying that a little bit, and let's zoom in a little so you can see that better. Simplifying that a bit, those threes will cancel. And I've got -250 over 4, which reduces to -125 over 2 plus 125. Well, that's going to equal -125 over 2 plus 250 over 2, which is positive 125 over 2. And that's going to be my X value. So those are the dimensions of this particular enclosure. That maximize the area while still spending only $500. Now I want to point out, if instead you had said the $1 per foot side was one of the X sides, you would have gotten the same answers, except you would have gotten X equal to 250 thirds and Y equal to 125 halves. That's what would have happened if you decided to write it this a little bit differently. Questions or comments or observations? Let me ask you all a question. If I had found the second coordinate of my vertex, what would I have been finding? Yeah, we're finding the area. Because my equation, where is it here? My equation area equal to -3/4 Y plus 125 Y times Y, or -3/4 Y squared plus 125 Y. My input coordinate is the Y value, right? Just the Y dimension here, and my output value is whatever the area is. And it's kind of, so here's what's kind of neat to see, and I think this is worth mentioning here. If you look at this right here, this area equation, this is just X times Y. So you could think about plugging in the Y value of your vertex, which is 250 thirds, to there and to there. But since we've also found X, you could just say, well, I know that if I plug in 250 thirds there, I'm going to get 125 halves. So if I plug back in Y to get the area, I'm just going to end up with, not surprisingly, X times Y. 250 thirds times 125 halves. That's totally what the maximum area would be if they asked me to find it. But again, I don't want you to do more work than you're being asked to do. So don't find the maximum area if you're not being asked to find it. Cool. Let's look at a few more. So the rest of these problems are really just, it's the same thing with a different spin. These are all kind of the same sort of questions, just asking us to look at it a slightly different way. So let's look at this one. Find two numbers whose sum is 18 and the sum of the squares is minimized. Note, the sum of the squares of X and Y is given by SS, for sum of squares, equal to X squared plus Y squared. Great, so they've already given us the thing we want to minimize. So we're trying to minimize sum of the squares equal to X squared plus Y squared. Great. All right, I want you all to try and write down what the constraint is. What is the limiting piece of information that we have to try doing here too? I'll give you a minute. You all on Zoom too. Try and see if you can figure out what the constraint is. Not really a math question, it's more of a reading question. All right, it's been about a minute. Before we conclude this, I just want everyone to see my fun new pencil bag. Looks like a monster. You close it, it's all like chill. You open it, it's like, okay. So anyway, much better than my old one that had pen ink all over it. Our constraint, well, we're told that the two numbers have a sum that is 18. So the numbers which we're calling X and Y, right? They kind of just made that happen for us. We could have chosen other things, but they said X and Y. Our constraint is that X plus Y has to equal 18. That is what we are limited by. So we couldn't pick 10 and 10 because their sum is too big. We're probably going to be picking 9 and 9 because that's probably often what ends up happening. The two numbers are kind of closest to each other. So we're still going to show the work. I'm going to solve for one of these. Let's do it the other ways, not the other, meaning let's not solve for X this time like we did last time. We're going to solve and get Y equal to, I should really not say solve. I like the word isolate better because we're not really solving the whole thing. We're just isolating one of our variables. So we're going to isolate Y equals 18 minus X, and we're going to plug that back in up here. So then sum of our squares is going to be X squared plus 18 minus X squared. 18 squared is going to be real fun. So let's see. So if I multiply this out, which I should, I get X squared plus 18 minus X times 18 minus X. So that's going to be X squared plus 18 times 18. Times 18. I don't know. Well, let's see. It's 9 times 9 is 36, 81 times 2 times 2. Yep, 324. Minus 18x minus 18x plus x squared. So simplifying this, I've got 2x squared minus 36x plus 324. And I'm trying to find the x coordinate of my vertex. So it's going to be a negative b over 2a, which is going to be a negative 36 over 2 times 2, which is 36 over 4, which is 9. Okay, so here is where it's easiest to make the wrong kind of move after this. If I want to find, well, actually, I should listen to my own words. I should go back and read the question because I've found the first coordinate of the vertex. What are they asking me to do? Find two numbers whose sum is 18 and the sum of the squares is minimized. They didn't ask me to find the sum of the squares. They asked me to find two numbers. So if X is 9, what's the other number have to be? Also 9, because they have to add to 18. So we're going to get Y equals 18 minus X, which is just 9. But I want to really kind of stress here, right? If you happen to start thinking about the other coordinate of the vertex of the other coordinate of the vertex, right? I really don't want you to think of it as V sub Y. It's the coordinate that is the sum of the squares. If you found the other coordinate of the vertex, I'm just going to do it to show you what you would get. If I plug in 9 for X, you're going to get 2 times 9 squared minus 36 times 9 plus 324. Let's see, that's going to be 2 times 81, which is 162, minus 9 times 36 is 324. So actually those cancel out, and you get 2 times 81, which is 162. Which is what you would get if you did 9 squared plus 9 squared. So, but right, that's not but that's not what they're asking for, right? We don't want to find Vy because that's not the second thing they're asking us for. We want X equals 9 and Y equals 9. Those are the two things we were actually looking for. So even though this is good to know, we don't actually need it. This is not a surprising result in that when you have, if you're taking two numbers that add to something and you want to maximize the sum of their squares, it is almost always the case that the numbers should be the same value, meaning they should need to be half of 18 in this case. That's very typical. And that's why I've asked the second question. What if the sum of the numbers, not number, sorry, I was typing that fast the other day, I missed another letter. What if the sum of the numbers was 7 instead of 18? So what if instead of having this situation where we have the sum of our squares is X squared plus Y squared, now our constraint was that X plus Y equals 7. If you had to guess, what would you guess the X and Y? And don't say words, just in your head. If you had to guess, what would you guess X and Y are both going to be? Think about it for just a second. All right, we've all got a guess. Let's see if we can confirm or disprove your guess, depending on what it was. I know what my guess is. Let's see. Do the same kind of thing. Y equals 7 minus X, and then I'm going to plug that back in over here. So now I'm trying to minimize, I can spell, sum of squares equal to X squared plus 7 minus X quantity squared. And so I simplify this. I got sum of squares equal to X squared plus, and to multiply this out, 7 minus X times 7 minus X is going to be 49 minus 14X plus X squared. And then simplifying this one more step, X squared plus X squared is 2X squared minus 14X plus 49. I do recommend writing your quadratics, whatever X squared plus whatever X plus whatever constant in the standard order, meaning highest power of X first, next highest power of X, then the constant, so that it is very easy for you to always see which thing is A and which thing is B and which thing is C. So here, there's our A is 2, and B is negative 14. And I guess C equals 49 if we care about it. All right, C always getting left out. So then the X coordinate of our vertex is negative 14 over 2 times 2, which is 14 over 4, which reduces to 7 halves. Or if you like a decimal, 3.5. I don't find this particularly surprising because just like before, when you had two numbers that were adding up to 18, we found that each of them being 9 maximized the sum of the squares. Sorry, minimized the sum of the squares. Minimized. Here, same deal. We have each two numbers adding up to 7, and each of them being half of 7 is going to be the thing that minimizes the sum of the squares. So just to kind of finish this off, we have X equal to 7 halves. And we do also have Y equal to, let's see, Y is equal to 7 minus X. So 7 minus 7 halves is 14 halves minus 7 halves, which is also 7 halves. So it's kind of nice to think about this for just a second. Any other numbers that, and it's easier for me and probably for you to think of it in terms of the first example, because it's easier to pick numbers that add to 18 than it is to add 7. If you pick any other two numbers that add to 18, their sum of squares is bigger than 162. So pick like 10 and 8. What's 10 squared? Wait, does that, yeah, does that to 18, right? 10 and 8, yeah. What's 10 squared? 8 squared? And you add this together, it's bigger than 162, 164. And that's true, right? If you go further away, like you pick like 11 and 7, 11 squared is 121, 7 squared is 49, 121 plus 49 is 170. So any other choice of numbers that add up to 18, if you take their squares and add them together, you're going to get a bigger result. Even if one of them is negative, especially if one of them is negative, right? If you pick like 20 and negative 2, 20 squared is 400, negative 2 squared is positive 4, and those definitely add up to a number that is bigger than 162. So the only way to really show it, though, is to actually do this kind of process. All right, here we go. So much time. Okay, I got two more problems to practice with, and then we will be done for the day. Here's another one, finding a point closest to another point. These are pretty typical. Like you will see problems like this in general, finding a point that's closest to another point. That's probably why I've given you a couple examples here. I don't know if there's any on, there's probably one on the homework. I don't remember now. I can't remember exactly, but let's do the thing. So when we want to find the point on the graph closest to another point, what we're really trying to do is, this means we're trying to minimize the distance between the point on the graph, which we don't know, and the point 8, 0. And I definitely think it's worth drawing a picture here. So y equal to the square root of x is a graph we are going to talk more about later, but it's a graph that's not too hard to graph. If we pick some points, you can pick x equal to 0 and you get y equal to 0. You pick x equal to 1, you get y equal to 1. I'm picking the nice values. I want to pick x equal to 2, although I mean that's a point on the graph too. You could have x equal to 2 and y equal to the square root of 2, but that's a harder point for me to plot. So I'm going to pick x equal to 4 and y equal to 2, because if x is 4, the square of 4 is 2. And the last point I'll graph on the graph is 7, 8, 9. If x is 9, y is going to be 3. So there are some points on my graph. It looks kind of like this. I mean, technically the graph has an infinite number of points on it. I'm just recognizing a few of them here, the easy ones. And then we're looking for the point on this graph that is closest to the point 8, 0. So I don't know exactly where it is. It's not a nice point. It's probably somewhere about right there. So that point that I don't know, I'm going to give it a name. And typically we're going to give points names like x, y. You can do a, b or something else, but x, y is pretty standard. So I'm trying to minimize that distance. So we want to minimize that distance, which we're just going to use the distance formula. So the distance between 2 points is the square root of the difference in the x's. So that x minus that x. You could also subtract the other way, but I do recommend that if one of them is a variable and one of them is an actual number, to do the variable minus the number, not the number minus the variable. I mean, it doesn't really matter, but I find it easier to do it this way. And then y minus 0 squared. Okay, but that thing has a square root, and we don't really want that, because the only things we really know how to deal with are parabolas, for lack of a better word. So instead of minimizing the distance, we talked about last time how, well, if you minimize the insides, which is just the square of the distance, you will still be minimizing the distance itself. So instead, and this is always the way to make it easier, even if you have other methods and techniques where you can use derivatives and all that stuff, still it's easier in your future to, instead of minimizing the distance, minimize the square of the distance. Like if you take, well, if you take away a few things from this class, that's definitely one of the things I want you to for sure take away. Is that when you have to minimize a distance, square it and minimize the distance squared. You'll get the same answer as far as the things that minimize it, although you do have to make sure you, like if someone said, what's the minimum distance? And you minimize the distance squared and then went back and tried to say what the distance was, you would have to take that number and take the square root of it so that you were actually finding the distance, not the distance squared. But other than that, it's pretty great. I mean, that's still fine. So instead, we're going to minimize the square of the distance, which is just x minus 8 squared plus y minus 0 is just y. So y squared. All right. And just like most of the other problems we're dealing with, we have 2 variables. We only want 1 variable. So we need a constraint. And when there's graphs, usually the constraint is that the point is on the graph. Meaning that point there, x, y, is on the graph of the curve y equal to the square root of x. Meaning that is your constraint, that y has to equal the square root of x. You have no other choice. So I'm going to say my constraint is that y equals the square root of x. So I'm just going to substitute in the square root of x for y. I'm going to rewrite this as distance squared equals, I should multiply it. We'll do it in the next step. We'll do it in this step. So x minus 8 squared, all right, like this is x minus 8 times x minus 8. And then I've got the square root of x squared, which if I simplify that, it's going to be x squared minus 8x minus 8x, so minus 16x plus 64 plus x. So that's going to be the distance squared is equal to x squared. Negative 16 plus 1 is negative 15x plus 64. Oops. All right. we've gotten to the place where we have essentially a quadratic or a parabola. So our job, once again, for the umpteenth time, is to find the vertex of that parabola, or at least the first coordinate of the vertex. So let's write it over here. The first coordinate of my vertex is going to be negative 15 over 2 times 1, which is 15 halves. Or if you prefer a decimal, you can write a decimal, or 7.5. So the x coordinate is 15 halves. And then I go back and read the question. I go back and read the question. The question says, come on, James. Where's it? Find the point on the graph. Great, we found the x coordinate. We need the y coordinate. So let's see. Well, the graph is y equal to the square root of x. So that's how I'm going to find y. If x is 15 halves. Y has to be the square root of x, the square root of 15 halves. And I would not try to simplify that, right? There is some rationalizing someone could do if they really wanted to. I don't think you need to do that. So I would just say the point on the graph that is closest to 8, 0 is 15 halves, comma, square root of 15 halves. So it's not like I couldn't have guessed that point, right? It's not an obvious point that's on the curve. It's not a nice point. It's not 9, 3 or 16, 2. It's a point that's kind of close to 9, 3, but it's not. There's other words I could say there. That one's not too terrible as far as things go. So when you're finding the point on a graph that's closest to another point, you're always just minimizing the square of the distance between those 2 points. And one point will always be the unknown point, so it'll be kind of an x, y, and the other point will be a given point, like in this case, 8, 0. Not too terrible. All right, last one. Time is it? 10:37. Okay, we might finish early. No promises. No guarantees. Last day of September. Did you see there's like a new what is it? A fun movie. Everyone like the spooky movie. Hocus Pocus. There's like a new Hocus Pocus movie. Hocus Pocus 2 on Netflix. No, probably Disney Plus, right? Probably Disney Plus, right? Hocus Pocus Disney. Anyway, there's a new Hocus Pocus. In case you didn't know, there's a new Hocus Pocus movie. Spooky season. All right. Enjoy it. Watch it. It's probably entertaining, mildly, moderately. For which point on the graph of the parabola y equals 5x minus x squared is the sum of the coordinates a maximum? Hey. Kind of a weird question. I'm going to draw some pictures. I'm going to draw this parabola just to kind of make life interesting. So actually, before we answer this question, let's graph the parabola. I'm not going to be super duper, what's the word I'm looking for? Precise about graphing this parabola. I'm really just going to find the x-intercepts because well, first of all, I know the y-intercept is 0. So I plug in 0 for x, I get 0 for y. So the y-intercept is 0. Which means one of the x-intercepts is also 0. Right? If your y-intercept is ever 0, you automatically have an x-intercept that is for sure 0. X-intercepts, set y equal to 0, you're going to get 0 equal to 5x minus x squared. I'm going to factor out an x and get x times 5 minus x. So I end up getting x equal to 0, x equal to positive 5. And I'm not going to find the vertex. I know I've said like 1,000 times the vertex is the most important point of the parabola. That is true, but I don't really care in this instance. So just believe me for a minute. It's really okay to not always graph the vertex. I'm still going to graph the vertex. So here are my intercepts, x equals 0 and x equals 5. And which way does my parabola open? Downwards, right? Because I have a negative x. I probably could have rewritten this as y equal to negative x squared plus 5x. So here's something that's kind of useful, I think. If I'm trying to graph a parabola and I'm maybe not doing like the best job ever of it, it is true that the vertex is always midway between the two x-intercepts. So if I know my x-intercepts are 0 and 5, I know that my vertex is halfway between each of those. So it's somewhere at 5/2. So I'm going to guesstimate it's about there and then draw my vertex, my parabola like this. Okay, so what we're trying to find is the point on the graph, x comma y, where we quote unquote maximize, right? I said maximize, find the point where the sum of the coordinates is maximized. So we're trying to maximize x plus y. I guess I could say you don't have to have it be equal to something. I guess we could write it to something. Let's say the sum of the coordinates, which is x plus y. That's what we're trying to maximize here. And I will tell you, it's not going to be the vertex of that parabola. It is going to be the vertex of a parabola, just not that one, which is kind of extra confusing, I feel like. Right? There's a parabola, but that's not the parabola we're trying to find the vertex of. So, I have a thing I want to maximize. There are two variables, which is always the problem. We need the constraint. Okay, I want you all to try to write down or at least think about what the constraint might be. It's definitely on the page somewhere. I'll give you a minute and 5 seconds. Or to write it down if you know what it is. Give you all the time. Sometimes a minute feels really long. So just in case. Good. Okay, so the constraint is that that point has to be on the parabola. So if I'm trying to maximize the sum of the coordinates x plus y, that point there is on this parabola, y equal to 5x minus x squared. Meaning that is our constraint, that y is equal to 5x minus x squared. And we're going to put that back in right there. So now the thing we're trying to maximize, which I don't really need to keep writing, I just find that I do, is the sum of the coordinates is x plus 5x minus x squared. Which, simplifying that, that's going to be negative x squared plus x plus 5x is 6x. So we're trying to find the vertex of that parabola, or specifically the x coordinate. So I find the x coordinate, v sub x is going to be negative 6 over 2 times negative 1, which is positive 3. And now what? Well, now we ask ourselves, what do we want? For which point on the graph is the sum of the coordinates the maximum? Okay, so we found the x coordinate. Now we're trying to find the y coordinate on the graph. So I'm just going to go back and plug in this x coordinate into my constraint. So we're going to get x equal to 3. And we're going to get y equal to, if I plug in 3 here, I'm going to get 5 times 3 minus 3 squared, which is 15 minus 9, which is 6. Cool. So that point on the graph, 3, 6, which looks like where I plotted it, which is not the vertex, right? The vertex is 5/2, something. That's the vertex there. The point 3, 6 is the point on this parabola that maximizes the sum of the coordinates. And now here's an easy question to answer. What is the sum of those coordinates? 9, right? 3 plus 6, 9. So so I will just say, this is not what we were asked, right? This is extra information. So extra information. The maximum sum of coordinates, or in other words, the sum of coordinates maximal value is 3 plus 6, which is 9, which I will point out, just to kind of reiterate the same thing again and again, is that would be the second coordinate of the vertex of the thing we maximize. So if you look at the thing we maximize, which is negative x squared plus 6x, if you take that 3 value and you plug it back in here to get the y coordinate, the second coordinate of my vertex is negative 3 squared plus 6 times 3. Okay, negative 3 squared is 3 squared and then negative, so it's negative 9 plus 18, which is positive 9. That's not a coincidence, right? Those are the same because, right, the second coordinate of the vertex is the optimized value of your thing. So here, the second coordinate of the vertex is the maximum value of the sum of the coordinates. So most of the time when people are asking you to maximize or minimize something, they're typically asking you for what are the things, the coordinates, the inputs, the dimensions, the whatever, that give you a maximum value or a minimum value. Most of the time, with some exceptions, they're not actually asking you to find the maximum or minimum value.